John Dweck, Director of STEM Education for the Office of the Fresno County Superintendent of Schools, will focus on what a strong mathematics program looks like in the classroom and at home. Time will be spent on what children should be learning, how they should be learning it, and what we can be doing to best serve in an equitable and consistent manner. Please welcome John.
Hello, my name is John Dweck. I am the Director of STEM Education for the Office of the Fresno County Superintendent of Schools. I've been working here at a county level for quite a few years. I enjoy the opportunity to talk with teachers all the way from preschool up through the secondary level. But the base of what I love is in the primary grades. I began my education career working at a preschool and have been able to move on from there with a great learning of what goes on at those ages, and have never forgotten how important that time is. So today we're going to be talking about numeracy for preschool and the primary grades and what that looks like. We're going to start off with a couple of puzzles to get you thinking. Engagement at a virtual level is not easy, so here's an attempt to get you thinking and get your mind going. When you look at this puzzle, this is a 3x3 grid, how many squares do you see? Some people think this is really easy. Some people think it's a smaller number. Some people think it's a larger number. How does your mind contemplate this? How do you count them? How do you group them? You can see on the right-hand side, there's a link where you can find this picture online, or you can simply draw it yourself. But what about if we're talking with younger kids? So let's think about preschool. How many squares are here? How many can you find? I don't want to give you the answer. I want you to think about that. I want you to experience it and get that learning time in. This isn't about me, this is about you. And then as students get older and want more of a challenge, we can offer them a puzzle like this. Now how many squares do you see? What do you find right there? So these are ways we can engage our kids immediately and get them thinking. But another way to engage our kids is by reading to them. And that's what we're going to talk about the bulk of today. Developing numeracy through literature, developing numeracy through our actions. In our preschool, we start by just basic counting, and we'll get to a point where we want to count to 10. So here's a great book. I'm going to share a few books with you. Russell the Sheep. I love the drawings in this book, and this is about how Russell cannot fall asleep, and he starts to count things. He counts many things. You can find the YouTube video to watch it yourself if you don't own the book. I won't even tell you if Russell falls asleep or not, but there's some special things that happen for him. The Icky Bug Counting book. This goes up past 26, 27, 28 into much larger numbers. But it has great pictures, and you'd love to share this time with your kids, reading about Jerry Pilata and what he has there. Books like 10 Little Fish are another one, a really popular book that can get you thinking about numbers, talking with these with your preschooler. And finally, 10 Fat Turkeys. All these books have basic counting that you can over and over again review with your children and get those numbers and think about how they work together and the progression of them. So let's look at some dots. How many do you see right there? You've probably heard of number talks. This would be a dot talk, which is under that umbrella. So you should have immediately realized that there were 6 dots. When you do a dot talk with your kids, you only need to ask 2 questions. How many do you see? How do you see them? So how many do you see? I'm going to assume you're saying 6 right there. But the question now is, how do you see them? What does that mean as you looked at this? So I would hope that some of you would say, well, I saw 2, 2, and 2 like that. Or maybe you saw 2 groups of 3 like this. Both answers are correct as long as you saw 6. Any other ways that you may have seen that? What about this one? 2 groups of 3 like that, kind of in a triad, triangle form. Let's try another one. I'm going to put some more dots up there, and I want you to immediately think about how many dots you see. So, what do you see? How do you see them? Think about that for a little bit, and maybe think about it on your own, or if you're sitting with some people, talk with your friends around you. So there are a certain amount, and how did you see that? Did you see it like this? That 9 can be broken into 4, 4, and 1, or it can be broken into this type of 4, 4, and 1. Any other ways you could break that apart? Think about it for a moment. I would want to give my students that chance to think about it for a moment. What about this? 4 and 5, perhaps that's how you saw it. or maybe 6 and 3. This is called subitizing. Subitizing is when you can see an amount and know how many are there. When you roll dice, you don't count the dots on the dice, you just know how many there are. But you get to a point where there are too many dots to just subitize, and you start to break it apart. For humans, that's around 7 or 8. So when we have 9 dots showing, we have to break it apart in our mind to recognize how many are there. We see instantly some groupings of dots or groupings of whatever object it is that you're talking about. So that subitizing is a skill that we can easily work on with our youngest of kids. Don't start at 9 with your preschoolers, but maybe you start with 2 or 3 and talk about how many dots are available right there. So you hold up the dots, you hold up the objects, and you talk about the amount. You practice your subitizing and how you break that apart. And that breaking apart is an important skill that starts to come into play as the students get older into the elementary grades right there. Take a moment. Think about dot talks. Think about dot cards. How could you use these with your students? What math is being done there? I'm going to give you a few seconds. I'll be silent to think about it. All right, let's come back together. One thing I mentioned was that we're breaking that number 9 apart. So when the number 9 gets broken apart, this is a way that we can do that. You can break that apart into 4, 4, and 1. 9 is the same as 4, 1, and 4, 4 and 5, 6 and 3, or 1 and 1 and 1 and 1 and 1. This is called decomposing a number, and this shows up in our primary grades, in our standards here in California at least, where we want to make sure that our kids can decompose a number. But this starts with subitizing and then moves into this area. So we want to make sure that our kids can decompose these numbers. It's an important skill, and we're going to keep building this throughout this 45 minutes that we're together. We want our kids to recognize the amount, but then also break it apart into smaller amounts because it becomes easier when we're dealing with addition, subtraction, multiplying, and dividing as we move along. A next step after our dot talks is to go into looking at it through the 5 frame. So many of you have tried using a 5 frame before if you teach the youngest ones, and this 5 frame is a precursor to the 10 frame. So how many dots are there? How do you know? These are simple questions for adults, but this is intense stuff when you're 3 years old, 4 years old, talking about these dots. It's exciting. We want our kids to be able to say, I can count them, 1, 2, 3, and we have them touch each one for that one-to-one correspondence. They can also recognize sometimes that there are 2 empty spots. And then if they know a 5 frame, if they're comfortable with a 5 frame, they can take it and break it apart in that way. That's 3 with 2 empty spots. Let's try this 5 frame. How many are there? And how do you know? Simple, right? But again, exciting when you're 3. How about this? This is an important way to show our students 1. That doesn't have to be in that beginning space, but it can be anywhere. Our numbers exist in many locations, and this is a quick sample for that. And what about that? How many do you see, and how do you know? 5. And again, they can touch each one and talk about that. A full 5 frame is an important piece for our kids to understand. Next, we'll go to the 10 frame. Common in many of our classrooms. How many dots do you see? This is where it can get a little bit juicier because they see 3, but how do they see 3? Think about how you know it's 3. If you were 3, 4, 5, I can see 1 on top and 2 on the bottom. I can see 2 on the side and 1 all by itself. Or maybe I just see 3 right there. Or maybe I'm 5 years old and I can say, I know it's a 10 frame, and I can see 3, and I know that there are 7 spots left. These are all great answers that we want to hear from our kids. That 3 can be 1 and 2, but in multiple ways. 2 on the side with 1 there, 2 on the bottom with 1 on top are all great ways to talk about what 3 is. How about the next one? How many do you see? And how do you see it? Consider what this might look like with a 4 or 5-year-old having this conversation, showing them, holding up a card that has these on here, putting this on the screen for the students to see, having this conversation about how you know. Do you see 5 across the top and 2 on the bottom? So 7 is the same as 5 and 2. Maybe you see 4 in kind of a square with 3 going off to the right. So 7 is 4, and 3. Maybe you see 2 plus 2 plus 1 plus 1 plus 1. Maybe you see 2 plus 2 plus 3. It doesn't matter as long as they do recognize that it's 7. That's the important one. Breaking that 7 apart and seeing what's there. So maybe now you're like, you know what, I just saw 7. But when I hear this guy talk about 2 and 2 and 1 and 1 and 1, I see how it can be broken down in different ways. So try it with this next one. How many do you see and how do you see it? 5. What makes 5? 3 and 2, 4 and 1, 1 plus 1 plus 1 plus 1 plus 1, right? All great ways to talk about what makes 5. Consider now, we talked about subitizing, just recognizing numbers. And now we talked about this subitizing in a 5 frame and a 10 frame, but also what it looks like to decompose those dots, those objects, those items. They don't have to be red dots. This might be something you can do physically with your children at some point, or maybe something you do virtually to just have a conversation and talk to them. It's also a great tool to give our parents, because our parents can be doing this also. I don't do this all the time with my own kids, but I could do it if I was told this is a good activity and can be part of the math time while you're at home with your child. Finally, look at that. There's our 10 frame. How do we know? There's going to be at least one child likely that says it's all full, so it must be a 10. Or they can say, I see 5 and 5, 2 plus 2 plus 2 plus 2, however they break it apart and do that. All right? This 10 frame, it's an important piece. Make sure that you use it with your kiddos. Think now, what might this look like with your students? What math is being done here? I'm going to pause for a few seconds for you to consider and contemplate these 2 prompts. Enough time to think about it? Let's come back together. One tool that I want to make sure that you have access to and are thinking about is Flipgrid. So I made a Flipgrid here. So take a moment, use your phone or any device. You can either scan that QR code on the screen or you can type in the website right there, that URL. This is all about making 7. I wanted you to think about what does it look like to use technology to have students decompose, to make an amount, to consider an amount. So have you typed it in? Are you trying it? I know these are all going to be saved, so you can check this out later on. But when you go to that Flipgrid, you're going to find a video or more. The first one is of my son, where he's showing how to make 7. And he's using 2 hands and the fingers on those 2 hands to show 7. Make one of yourself. We can all put one on there. It only takes a few seconds to do it. You can simply be a part of this. You can use this with all your kids to have them show you how to make a certain number or respond to a prompt, whatever picture you put on your own Flipgrid. This is free, easy to use, and you can have those videos available to do a quick formative assessment and know where your students are at. Have you had a chance to go there yet, or have I been talking too much to consider this? I'll give you a few more seconds to see if there's videos on there or make your own. All right, so think about this. What might Flipgrid look like for you? If you could encourage your kids to make a video, my kids just use my phone or my wife's phone when they do it. So they can make this Flipgrid, they can answer the question. It's a great tool. So consider, what do these tools look like? How can this best be used for your kids in a virtual setting or in the classroom? Either one to do. This could be a center that they come to, or however you want to use it. I made another Flipgrid. This is one you can try out also. You might be able to tell from the URL that I created that this is about show me something in your house that is square. So again, I asked my son, he's just looking forward to going into 5th grade, so this was pretty easy for him to find something in the house that is square. He ran over and found 2 different shapes. One of them is a rectangle, one is a square. What has 4 sides to think about? Okay, Flipgrid, great tool, great way to engage your kids virtually when you aren't able to be in front of them and talk with them and interact with them. All right, so now I want to talk about some of the details of what goes into how we learn. This book was written a few years ago by David Souza. It's wonderful. I prefer to read fiction. I like a book where someone's in peril, there's an issue to take care of, there's a story to go through. But I'll pull out the nonfiction books sometimes, and this is one that drew me in and I read fully. Part of it might be the large font and lots of graphs and pictures. So when you look at this, I want you to think about This book talks about what happens in the mind of a child as they learn mathematics. And you can see on the slide, there are 5 stepping stones that are pointed out in here that allow us as the educator to really understand where our kids are at. I want to just go through here. I'm going to give you a chance to read the screen. And here's the first one. So take a moment and read that to yourself. These are the students that can see an amount. They don't necessarily know how much is there or if it's a great amount. We know that our youngest ones are just happy to have one thing in their hand. So they haven't gotten to the point of more or less. They're just happy to have what they've got in their hand or near them at the time. They're not comparing yet or thinking about that. The second step, though, I'll give you a moment to read this. So this is where we're starting to actually get some concept of amounts and the terms that we talk about. So this is where we start to get a little bit of like, he has less than me, she has more than me, and get those amounts are coming together to mean something. We're not necessarily adding things together, but we can definitely tell that there's a difference in what's in front of us and what's in front of somebody else. Here's the third one. First of all, they don't use the gingers on both hands. They use the fingers on both hands. I apologize for that typo right there. But let's talk about this. This is a time where the kids can count up to solve something. We all have seen kids that can't start counting like, here is 4, 5, 6, 7. These kids start at 1 and move up from there. They're in those basic numbers where they're really up to about 5, and they make mistakes as they get higher. We all know the numbers that kids tend to get confused on or skip over when they're doing that. But this is where the hand comes to be very important, and also why we have a base 10 system and why we use the 10 frame, because we have 10 fingers as we do this, and we're using our fingers as that first manipulative to figure things out. Here's the fourth one. So this is the time where our kids are actually really starting to get some meat to what they're doing right here. We're excited because they conceptually understand what's happening right here. So we're able to look at the digits in a problem. We're able to count on, which is a big deal that we celebrate that one. If you've ever dealt with counting on, you know what a celebration that is. And the fifth one, our kids are adding, we're beginning to subtract and piece those numbers together. So I want you to consider in the spectrum of where all of our children are, they're at different points in there. But it's good to remember what comes first, what comes second, and what the levels are at that our students are struggling through as we develop lessons, activities, centers, and stations for them. It's important to think about how the brain learns. Let's consider a song now. 5 Green and Speckled Frogs. I would sing it for you, but I don't want to torture you with that. You can sing it to yourself right now. The words are right there. This is a great math song to be thinking about subitizing and decomposing. They can look at the picture and see how many frogs there are, but let's really get in deeper with the decomposition of what's happening here. There are 5 frogs. Well, when one of them jumps into the pond, into the pool where it's nice and cool, how many are on the log? 4. How many are in the pond? 1. So 5 can be broken into 4 and 1. You sing the song again. Now there on the log, there are 3. In the pool, there are 2. So now the 5 is broken into 3 and 2, and then 2 and 3, and then 1 and 4, and then 0 and 5. So this song is a great thing to be talking with your kids about. 5 is 4 and 1. 5 is 3 and 2. 5 is 2 and 3, and et cetera, et cetera. So think about songs like this and how you can break that apart and look at it, because this symbol right here is a really important one. If I'm going to write the number 5 on the board and I put the equal sign after it to the right, I'm really throwing off some people. Consider this. We tend to give our kids math problems where it is 4 plus 3 equals 2 plus 1 equals 10 plus 4 equals. This makes the math sometimes seem like a magic problem, and we say, ta-da, at the end, I got what the answer is. But we don't connect it to the original problem. We want our kids to really be thinking about the fact that that equal sign is like a balance beam. It's the fulcrum of what's on both sides there. So instead of always saying 4 plus 4 equals 8, we can say 8 equals 4 plus 4. Remember, most of us grew up where the equal sign was always on the right, where it was traveling to the side and we got our answer at the end. And then all of a sudden we got to algebra or pre-algebra and we had to solve for y. We had to isolate the variable. So the y went on the left and then the equal sign, and we did all this work. And none of us really understood about if that was like mathematically legal to do. We were thrown off by that fact. So if we start at a young age where the equal sign can go on the other side, can go on the left, 12 equals what? What equals 12? 9 equals what? 9 equals 4 plus 5 equals 4 plus 4 plus 1 equals 3 plus 3 plus 3. What else does it equal? Think about that for a little bit. Here's an activity you can do with young children. So here I had 2 pieces of paper and I had 8 squares. 8 squares? 8 squares. So the student had foam squares and they would hold them in their hands and they would drop them and see how many bounced into either paper. And then on the whiteboard that you can't see in this picture, that was just off to the side, there was a number 8 written across the top. And the student could now write 6 plus 2. Then picks up the squares again, shakes them up, drops them, and write what else 8 equals. Sometimes it's the same thing, 8 plus 2. Sometimes it's 2 plus 8. Sometimes his hands purposefully are to one side and it's 0 plus 8. It doesn't matter. We're just talking about how to decompose that number and what that looks like. Activities like this are super important to get kids breaking things down. So I recorded a few videos with my son. He's the youngest member in my household. So I didn't have a 5-year-old, but I do have a 10-year-old. So I'm going to show you some videos that talk about the math with him. The first one is about the difference between 4 plus 5 versus 6 plus 7. Which one do you think is easier? Why do you think that one is easier? So I didn't prep my son for this, and I just pulled him up to do it and asked him these. So you're going to watch these videos that have no practice and are a little bit raw, filmed in my house with my phone on a ladder. So let's take a moment to watch the video and see how it goes. All right, well, welcome to this video, and we're going to talk about these 2 problems right here. So Levi, we've got 4 and 5, 6 and 7. Point to the one you think is easier. You think this one's easier. Mm-hmm. Most people think that one's easier. Why is this one harder?
It's not.
Well, you said this one's easier at a glance, so why would this one be harder?
Because you have to regroup.
Ah, all right. So this one, we know the answer to this one's going to be 13, and the answer to this one's going to be
9.
So people don't like having to regroup. They don't want to have to carry the one or break things apart. So tell me how you solved this one.
4 is 1 away from 5. So 5 plus 5 is 10, and then minus 1 is 9.
5 plus 5 is 10 minus 1, and that's because we added 1 right there. So 4 and 1 is 5. We brought that 5 down, and that's 10. But now we need to subtract that 1.
Right.
So we subtract the 1 from there, and that gives us 9. And this is some messy note-taking because we almost made this look like a fraction, but when we're just talking about it, we can deal with that. So now, tell me about 6 and 7. At one point, you're like, well, it's not any harder, but it's not as easy as this one. So how would you solve 6 and 7?
With 6 and 7, I know that 6 is 1 more than 5, and 7 is 2 more than 5.
All right, hold on. Let's write that down. So this is 1 more than 5, and this is 2 more than 5. Okay?
Yeah. So then if we take the 5 and 5 plus equals 10.
Okay.
And then we take the 1 and the 2 equals 3. 10 plus 3 equals 13.
And a lot of people will say that when you look at these problems, 10 plus 3 or 6 plus 7, we both know they're 13, but this one is easier because this one we can just say the 3 and the 0, that's 13. Whereas here, there's a little more manipulation that has to happen. Some other ways that people will solve 6 and 7 is they'll say, well, I have the 6 and I have the 7. I can add 1 here, and that gives me doubles. So 7 and 7 is 14, and then subtract the 1 gives me 13. Or the opposite way is they can say, well, I have 6 plus 7, I'll subtract 1. Now I have 6 plus 6, that's doubles.
That's 12.
And then I just add this one back in, 12 plus 1. And really, look at 12 plus 1, 14 minus 1, 10 plus 3, 6 plus 7, they all equal 13. What do you want to add?
If you do both methods, you would find the one that's in between, and that would be your answer.
Very nice. Tell me more about that.
If you did, there would be this would be the original problem, and then there would be 7 and 7, 6 and 6.
Right.
There would be no in-between section, which is 6 plus 7, and that equals 13.
Right, because we have the 14 and the 12, and 13 is right in the middle.
Because it's in between the doubles.
So we can manipulate these numbers all we want, and really we're starting to get into what we talked about earlier with what makes 13. What makes 13? We already have right here, 6 and 7, 10 plus 3. If we just stick with addition, 12 plus 1. And if we want to jump into subtraction, 14 minus 1. Tell me one more way using addition to make 13.
One more way is using addition.
Yeah. I put you on the spot.
3 plus, wait,
Wow.
10.
Okay, but that's the same as this one right here, which is good because that is one of the properties. The additive property is addition, and then the commutative property means that we can do 10 plus 3 or 3 plus 7 and get the same answer. So that's a good point to mention that. Can you think of another way to make 13 by adding? We've got these right here. Are you stuck?
Yeah.
What if I told you 3 plus 9? Does that make 13?
No.
What do I need to do?
You need to make the 3 a 4.
So I could do 4 plus 9, but fix this one. How much more do I need?
1 more.
Can we have 3 add-ins? Is that okay?
Yeah.
Yeah, totally okay. All right, so
I have another one.
tell me one more.
1 plus 1 plus 1 plus
Oh.
1 plus 1 plus 1 plus 1 plus 1 plus 1.
I'm going
plus
to use
1
the
plus 1
ellipses.
Plus 1 plus 1.
I'm going to use the ellipses and maybe with the lazy way like that. But thank you for helping us talk about why 4 and 5 is sometimes easier than 6 plus 7.
Bye.
So what do you think about that? Did you agree with him? Is 6 plus 7 more difficult? He's 10, so neither of these are difficult, but he broke that down and thought about what that looks like. Did you see decomposing? What did you learn from watching this 10-year-old solve the problem with dad trying not to jump in, but having some great ideas right there? Consider that for a moment, either on your own or again with those that you're sitting by. All right, I've got another video. This one is about 17 plus 16. Before we watch the video though, I want you to take the time to add them yourself. How do you add 17 and 16? What do you do to add 17 plus 16? Find some scratch paper or do it in your head? I learned to do this kind of thing purely algorithmic. The 17 goes on top, 16 goes underneath. Do you do it that same way? Or is there another method that maybe you use? Did your teacher show you something different? Did a parent show you something different? All right, let's watch the video. We're going to talk about 17 and 16 now, putting these together. So basic way to do this would be the standard algorithm, and that is taking 17 and 16. We always tell our kids put the higher number on top. That's really not important, but we always do that. 7 and 6 is 13. We regroup the 10 We don't want to say carry the 1 because that doesn't have any math behind it, but we regroup the 10, and 1 plus 1 plus 1 is 3, or 10 plus 10 plus 10 is 33. Levi, how do you want to solve this problem?
So, can I use the...
Sure, you want to write it out?
Yeah.
Go for it.
So, 6 plus 7 is 13.
Yeah.
And then if you add the 2 10s to the 13, right here, I got the 20 because of the 2 10s in 17 and 16.
Okay.
So 20 plus 13 is 33.
Nice. Let me see that red pen, because I want to point out that you took this, I'll put them like this. I'll put the 16 and 17 on top of each other like this. You said this is 10 plus 7, and this is 10 plus 6.
Yes.
And then you added those first, and you said the 10s, and that's 20, and then we added those together and got 33. What you need to be thinking about here is the fact that earlier when we were talking about dots and when we were talking about the equal sign and what that means, when you understand that 17 is 10 plus 7, you can break that apart. That's decomposing. We used the word decomposing earlier, and that shows up in the kindergarten, first grade standards, where we want kids to be able to decompose numbers for better understanding. So this goes back to our dot talks, where we say, how do you know that is 6? How do you know that that is 9? And you break those apart. So now we're breaking them apart for the purpose of adding these together. So if we can break this apart, he is able to say, I've got my 1s, I'll add those together, and then I'll add my 10s together like that. Is there another way that you could solve this? Think about it. What else could you do to solve this problem besides breaking it apart, or break it apart in a different way that's easier for you? Maybe you grew up or were told a different way, or maybe you simply did this way and now seeing this is a little bit mind-blowing to you. But these are great methods to use as you try and solve basic problems like 17 plus 16. Any addition problem can be broken apart. It's also why we do this kind of action with our kids. We say, I want you to take 342 and write it in expanded notation, 300 plus 40 plus 2. I did this all throughout elementary school. I had no idea why, and I don't think my teachers knew why, but for some reason we broke out into expanded notation. Now we can talk with our kids and say, let's do expanded notation and actually think about how the numbers fit together. This right here is our 13, and we break that apart into 10 plus 3, and this 10 is what is right there. So when we say carry the 1, we're actually carrying 10, but we're really regrouping that 10 to put it in the tens column. This is where place value comes for reals. So when you think about, my kids struggle with place value, my kids don't understand place value, do this. This is what teaches place value to your students.
It's actually really easy when you know it.
I hope you enjoyed that one. So when I was growing up, like I said, I only learned to do things with the basic algorithm. I had to line things up and add them down. It wasn't until I was in college when all of a sudden I started to learn about different ways to solve these problems. And it was eye-opening to me, mind-boggling. Then I met my wife, who's got a great number sense, and she did the same thing. She broke numbers apart comfortably and just ran right through them. So I was super impressed and thought, what kind of math power does this woman have to just break things apart and talk about them so simply? So it was through my college experience, becoming a teacher, and also talking with her about how did you learn to do this? She learned it from her dad, who had great number sense also. But if we don't push ourselves to practice these things, we tend to just fall back to the basics. So we play a lot of games in our house. And whenever we do this, I try and push myself to add numbers in my head and break things apart in the most simplest way possible. We're going to try 2 more problems. So the next one is this, 22 and 18. Not too difficult. Maybe you know the answer already quickly, but why do you know that answer quickly? Let's watch the video and see if you came up with the same thing. So now we're going to talk about 22 plus 18. So think for a moment about what you just did. How did you solve 22 and 18? A lot of people will look at this and think, well, I know that 8 and 2 make 10, so it's going to end in 0. And a common wrong answer is 30 or 50, where they go down too low or up too high. And so the answer is 40. What I do is I say, well, I can see that this is only 2 away from the answer that from the add-in that I want. So this is almost 20 plus 20, and that's 40. But I got to make sure and verify that by looking at how these numbers fit together. This is 22 minus 2 is 20, 18 plus 2 is 20. So if I have minus 2 plus 2 in the same thing, I don't have to do anything else here. I'm done, and I can check that. That's a really common way. This is compensation to make that happen. You'll see this happen in a problem like 22 plus 21. When we've done some similar problems to this, this is close to 20, this is close to 20, this is minus 2, this is minus 1. That's 40. But now I got to deal with this and add back in my 2 and my 1, which is 3. So the answer is 43. So making these into friendlier numbers, happier numbers, comfortable numbers, whatever kind of numbers you want, is a really good strategy to talk with your students about. If you don't like the number, find a number that you do like, but understand you have to compensate for that throughout the entire problem. Did yours add up similar to how we added it? What did I do in there? I apologize that my son wasn't in this one. He dropped out after the first 2. Was your method one that I showed, or do you have an additional method? Because you want to draw these out from your students and talk about this with your students. Post this for them. Use the Flipgrid for them to show that. Let them comment, talk, and think about different ways to add these numbers. But we have to be shown them sometimes first what the different methods are. If a student comes up with a unique method, let them be the ones that name it. Name it after that child. We had a method in our house that was named the Isaac method. Let it be that way. Let it be their method to own. Let's try one last one. 35 and 17. What a horrible problem. You know you're going to have to regroup or carry, whatever you want to call it regrouping. So try this one out. Think about it for a little bit. I'll give you a moment to just consider the problem. All right, now we're going to watch the video. All right, so how did you solve 35 and 17? What method did you use? We've talked about compensation. We've talked about expanded notation and doing some different ideas to get that cleaned up. So now we're at 35 and 17. Let's see if I can come up with what you did. So I'm going to start with the basic algorithm. I can do 35 and 17. 5 and 7 is 12. Carry the 10. Regroup the 10. The phrase that makes sense is regrouping. The phrase we fall back on is sometimes to carry. 10 plus 3 plus 10 is 50. So 52 is the answer I get when I work it out that way. Now if I want to do it through expanded notation or decomposing, I can say 35 equals 30 plus 5, 17 equals 10 plus 7. Here are my 1s, 5 and 7 is 12. Here are my 10s, 30 and 10 is 40. And when I add those, this is a much simpler problem than 35 and 17. I would much rather solve 40 plus 12. So 40 plus 12 is 52. And you may want to put it in the standard algorithm form or just leave it like that. It's your choice of which method you want. Some people will also take this, I'll get a different color and say 35 and 17. Well, this is fairly close to 20, and 20 plus 35 is easier. That's going to be 55. That's where I added 3, so now I'll subtract 3. 55 minus 3 is 52. Something to consider is to think about where do some of these numbers show up over and over again. We see 12, we see 40, we see some of this, we see 35 in different places. So where do you tend to see the same numbers as you pull it apart, put it back together, and manipulate that? Those are great conversations to have with your students also. Did you get something out of that? With the numbers shown in a different way than what you're typically used to? Hopefully you got some numbers going through your head. You're considering like, well, maybe this is easier. Maybe this is more difficult because just that algorithm is your style. But Don't limit yourself to how you solve these problems. We want our students to have multiple methods for doing this, not just one method, but many ways. There are a lot of ways to get to this answer. Let's not limit it to a right way or a wrong way, but if they get the right answer and you can generalize it, that works, and that's good math. That gets our kids thinking that math is problem solving, not just memorization. If math is about memorization, they're not going to enjoy it. Math is all about memorizing for me. If I couldn't keep it in my head, then it was gone. Once there were so many rules, too many to memorize, thank goodness in high school they let me have a note card that had rules on there. What a joke. What's the point of memorize all these things when I only need it for a test and then I forget about it? It's the same idea in history. Don't just memorize dates, but memorize what happened and the series that was going on. Think about this at a deeper level. It lets our kids enjoy the math, experience the math, and want to do the math. So consider everything we did today. Subitizing, decomposing, breaking these things apart, and looking at the math from a different perspective right there. We have some great points here. Let's think about universal design for learning. We want different tools for construction and composition. So when these kids are expressing what they do, let them do it in different ways. It gives them that tool, that mindset, and that strength to be able to answer these questions, not just how you tell them to, but how they want to, and solve it. Also under universal design for learning, we want to think about multiple means of engagement. When we allow our kids to come in at their own place to solve problems in a way that they are comfortable with, again, not just memorizing, but problem solving, that gives them some choice, lets them realize that they have some strength in that, and that's going to give them a better mindset towards enjoying the mathematics that's in front of them. I also want to touch just quickly on our math practices. These are a part of our state-adopted math standards. Math practice number 1, make sense of problems and persevere in solving them. We can do this with simple addition if we make it more about the solving part and not just about the answer part, thinking about how those numbers fit together and what those look like. And that fits also right into math practice number 7 with structure. How are you solving it? What patterns do you see? How does it come together in comparison to other problems we solve and other methods of solving that same problem? These are all great tools and things that we can bring in for our children. So now think about what squares up for you. You agree with that. Also think about what are some things that you have questions about, you wonder about, what's spinning around in your head right there in the bottom. What squares up, what spins around in your head still, and finally, do you have 3 questions that you might want to wonder? What 3 questions do you have? Consider those things, think about them. Maybe you'll email me, maybe you'll talk to a friend. Maybe this will be a good conversation to have with other professionals that you work with and interact with. So consider all of this as you move forward with a good numeracy mindset and numeracy program as a part of your overall math program. If you have questions, if you have comments, talk with your colleagues, talk with other people who are attending this conference or maybe who weren't able to attend this conference to share what you've learned and what you're thinking about doing. You can always email me, contact me with questions, comments, thoughts. We all want to get better. I do too. So let me know what you're trying and send me pictures or videos because I would love to be able to learn more and get better at what I do too. With that, have a great rest of your conference, and I hope you fully enjoy this day.